Okay, I'm going to try one last thing.
No, it's working.
This is fine. Don't touch it. All right, fine. Okay, good. So, here, so to go on to part two. So I have a somewhat meandering agenda. Now, why isn't it up? It's not moving. Great. What happens if I do this? See, I can see things changing here, but I'm not succeeding in. Let me try one last time. So, more your screen. This time, I'm just going to. Can I share everything? Screen one. All right. Yes, I can share. Okay. Why is that? What do you see now?
The wrong screen. I think we've got what you've got here on your right now.
That's what you see?
Yeah.
Okay. Let me try this high floating meeting controls. It won't do the slideshow. What am I saying? All right, one last time. Let's see what happens. Now, am I in the meeting or no longer?
No, you're still in the meeting.
I'm still in the meeting. Okay. No, I don't see the controls, which is a problem, but.
And you're sharing your screen still at the moment. So,
Okay.
right. You just try play, see what happens. It's sharing the wrong screen.
Yeah. Huh? No? Is it wrong again?
Yeah, we see both slides, this one and the next one.
Okay, that's because now I'm sharing the whole screen, which I should not be. I'm also not sure why it suddenly decided to share screen. Floquet phases, PowerPoint slideshow. Any better?
Yeah.
Yeah. Yeah. All right, and moved?
Yes.
All right, finally. Okay.
Now.
Okay, good. Quickly. So here's the plan. And what happened to the pointer?
Another one. That's
While that shows up. So here's the plan. I want to offer some general comments and time crystals. Then I want to get back to the discrete crystal phase and talk about its absolute stability. Talk about experiments, and then end with a sort of a forward-looking, hopefully, set of comments on where I think all of this is going. Right. Okay. So, oops. No, why am I missing this? Oh, no. Gosh. I'm sorry. I don't know what's going on. Hide. Be with you in just a minute. I'm not really sure how this happened. Okay, I think I'm good now. So let's try again. Now you'll have to tell me whether it's sharing or not.
Not yet.
Not yet, okay. Means something's wrong, such as share screen. This is share. Working?
We'll see when you finish your presentation. You're sharing the one with
Oh, God. PDF was a lot easier, wasn't it? Maybe I should have just. I mean, it shows me 3 possible windows. There are actually 4 of them, funnily enough, as options. So I honestly have no idea what I should be doing.
That was good.
That's good.
That's good. Okay, but I think the question. No, I don't think I can. No, I think some other one I ought to be sharing. Oh, God. PowerPoint slideshow, PowerPoint, Floquet, okay. If one of you will come and look over my shoulder, because I may be running around in a, so Andy, will you come and just follow me? So if I do something really stupid, you'll stop me. Okay. So observe that my options are screen, which I think doesn't work. This one, which is screen 2, this one, which is a, right? And then, so there are all these options. Why there's so many, I have no idea.
I don't know.
Okay, so let's try a slideshow, right? Or let's
We try that one.
try that one.
No,
So that, okay, share. And then
Well, and actually have the same problem. I'm not function fixed it.
wrong again?
Yeah, but yeah,
Okay,
it did work.
okay, so that one didn't work. So
Disable the presenter view somehow.
let's try this one.
Yeah.
How's that?
That's the right window.
Okay,
but it's different from the one that you have shown here. Does it show in this?
yeah, but if, see, this one doesn't start as,
No,
then I can't advance.
no, because the thing on here is what's showing.
Right, what is showing there? Okay, that's helpful. All right.
Maybe just mirror screens if you can get away without using your presenter view.
That one didn't work.
Can you advance it now?
Right now,
It's crashed or.
no, the thing is, I'm nowhere near the
Ah, so this just says it's screen 2. So maybe we
oh,
want
it's
to
screen 2. Okay. So
no, that one maybe. But
no, but the point
Yeah,
is,
this is good here.
I know, but it's just showing one slide. We're not really sure. I think it's the PowerPoint rather.
Yeah.
I would
think
restart,
PowerPoint is crashed.
close the PowerPoint and reopen it and see what.
I did that a minute ago. All right, let's try again. Second.
I should say too, Shivaji, I would have to leave in the end.
Just don't leave before I have the screen sharing up.
I will not be. I'll not leave before we begin. Well, I hope not anyway.
Those of you, this is not the beginning of the end. This is not even the end of the beginning. All right. So now what? I can try and share. Okay, what are my options? Screen, which I don't want to do. This one, I hope.
Oh, I'm not plugged in.
I haven't, yeah, but
Yeah.
that somehow should be secondary, right? That's not what the Zoom is about.
I think that's working here,
Okay,
but
and
it's
now
not on that. screen.
I've just advanced. Did it advance?
Yes.
If you just watch it on Zoom.
It's the next one along.
Perfectly good on.
Okay.
Yeah, that's good. And this is right.
Oh, now I hope I didn't
Bravo.
do anything else to any of the other slides. So hope for the best. Okay, right now I'm not going to touch anything for a minute, then I'll get rid of this and see. Okay. Oh, no.
Right.
Yes, but the slides that I went to all the trouble to put in have disappeared.
Bring it.
Wing it. Okay, I'm going to wing it in the following way. I just need to hold it at least for myself to see, and I'll wing it from there. Okay, so what's a time crystal? And then I'll come back to this. One definition of a time crystal is that it is a macroscopic conservative clock. Okay, so it has to be macroscopic, conservative in the sense of it should not use net energy, because we all know clocks, right, which are plugged in and run just fine. And it has to be a clock. It needs to have a natural cycle where it repeats within a certain period. So the question is why the name? And so the name arises, right, from the idea that if you have an underlying dynamics, which is time translationally invariant, now what? What do you see? No?
What is the time crystal?
On the,
You-
I'm not
you-
seeing it on Zoom anymore.
Not on Zoom anymore, but you see it here.
The wrong side, but let's just do this thing.
Just do it.
Yes.
Okay, sorry, but we'll just, yeah. Okay. At least you can see it, whereas previously nobody could see it. So I think it is improved, but- okay. So the rules underlying the clock are time independent, right? And therefore time translation invariance, but the motion of the state is not. So this is analogous, of course, to other broken symmetries, such as translations. And so if you break translation symmetry, right, you get something that you might call a crystal, a charge density wave, but let's just call it a crystal. And so the name time crystal, I guess Frank Wilczek coined it, was to build on that analogy. And specifically, of course, it's not just that you're breaking time translation invariance, but you're breaking it in a periodic way. And of course, if you broke it some other way, you could imagine you get a time glass or a time quasi-crystal. It doesn't have to be a time crystal. Okay. All right. Now, of course, it's not like people hadn't ever thought about things that just run forever without, right, using energy. That's the whole history of the perpetual motion machine. And so you might say, if you just want a large clock, what's wrong with a large pendulum or a grandfather clock? So there are two problems with it. So the first is, of course, there's the problem of friction. You have a clock with some friction, so you start it off and it's going to lose energy and stuff. Now, you have to decide on something, and we're going to ignore that one, on the thesis that, it's a little easier to imagine sort of controllably sort of getting rid of it. And of course, anything that you observe, any phase of matter has some limitation if you decide to be really, sort of perverse about it. My favorite example is take a superconductor, which everybody agrees is a phase of matter. But if you make a superconducting sample, which is of the size of the Earth's orbit, well, it turns out that if there are monopoles in a grand unified theory, this will become a problem with the superconductor. Okay, so you can't have an infinite superconductor. Okay, but the second problem is actually more interesting. That has to do with the second law, and which is that if I had a pendulum, or even if this rod was rigid, so we're imagining this motion, but really it's got all these degrees of freedom, and statistical mechanics / thermodynamics tell us that in equilibrium, in fact, you ought to be calculating with all those degrees of freedom in there. They will all be populated, right? And so what will happen is that even though we started it off like this, it's going to transfer energy to the other modes till the equilibrium state is reached. So even if there was no friction, you come back in a sufficiently long time, it'll be sort of more or less vertical and shimmering because the initial energy will improve this way. So that's the macroscopic aspect. When you write a single equation of motion with 1 degree of freedom, what you've done is you've caused all sorts of other stiffnesses to become infinite, so that none of these other modes can be excited. But that's then very, so that's the sort of artificiality that we don't want to, look at. Okay. Now, so that's the sort of history of the perpetual motion machine. Actually, people had decided that they wouldn't work even before thermodynamics was clearly formulated, but when it was kind of obvious that this might be good. Now, Wilczek in 2012 sort of came back to this, and his initial paper or two really had to do with quantum systems at zero temperature, and you could say, well, maybe the quantum system at zero temperature really hadn't been considered before. So it was certainly something to think about. And one of the intuitive pictures he proposed, for example, was what if the ground state of a system on the ring has a moving solitron? So there's a solitron that likes to move. Well, then, as you stand, sort of blip, blip, blip. So there should be some time dependence. So, and then there will be periodic oscillations. So he suggested this, and there were, of course, the immediate objection, was well, it's in the ground state, it's an eigenstate, and if it's an eigenstate, then of course the expectation value of any operator must be independent of time. It's a stationary state, right? So of course the immediate counter to that is, well, look, that's often true of symmetries, which is to say that there is some state which is symmetric, and even is naively symmetric. So even in the broken symmetry phase, if you take the naive state, it looks symmetric. That doesn't mean that symmetry is broken. You just have to look more carefully by looking, for instance, at correlation. So in the case, let's say, of an Ising magnet, asking for the expectation value of the spin may not be the right question to ask, but if you ask a 2-point function, if this is up, then is that up, right? That would be the distinction between a paramagnet and a paramagnet, even when the state is always naively symmetric. Okay, so the question was, maybe that was true of time translation invariance as well. All right, so as an example of how, now this can be subtle, is consider just our friend, the harmonic oscillator. So, so obviously in any eigenstate, the expectation value of position is 0. On the other hand, and so that doesn't tell me that anything is moving in time, but if you drive a harmonic oscillator at some frequency omega, and that approaches its natural frequency, then you get an infinite susceptibility, right? So that's like having a magnet and applying a field at the right momentum, and all of a sudden you get a huge response in the broken symmetry phase, and that's how you know that it's really trying to break the symmetry. You just, stupidly can't see it. Or you could study the 2-point function, and you will find that it oscillates. Finally, you could actually make coherent state to the harmonic oscillator, which would happily do that, right? And then now, of course, the oscillator is very special. There's only one frequency, right? All energy differences are just multiples of h bar omega naught. And so general non-eigenstates are periodically the same frequency. That isn't going to happen for a more complicated spectrum. But nevertheless, it gives you an example of how a harmonic oscillator in its eigenstates doesn't show any time dependence, but all the signatures that it's really trying to oscillate are there. So the question is, can this happen from macroscopic systems? So after we'll check, there were no go results from Bruno, Maziers, and Watanabe and Oshikawa wrote a paper in 2014 saying that this couldn't happen. And so I want to ask, what is it that these results actually ruled out? So the Watanabe Oshikawa paper considered 2-point functions of operators which are localized at x and y, right? So one is you look at equal times and you sort of see how things evolve in time. Actually, I don't think this is right. So one of them should be zero. Yeah, it should be this. Both of them should be zero. Sorry, it's different locations and it matters. So they asked the question, which I think should probably call spatiotemporal order, which is to say you're looking at distance, locations, and long times, and ask, is there an oscillation? And they showed under certain circumstances that couldn't happen. But they were looking at the ground state. They assumed that they had the Gibbs state for a Hamiltonian. What it did not do was rule out a non-constant dependence. For instance, in looking at a point and looking just later in time, right, sort of nearby, which it turns out can happen, and in many body localized systems, where in fact it looks like kind of a glassy behavior. And it did not rule out non-constant time dependence in states with a finite energy above, the ground state. And I can give you a very, very simple example of it. Imagine that there is a classical crystal and it's moving past you, and you're standing here, right? So that's you. There's the crystal moving by. So of course you're going to see blip, 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 right? As each atom goes by. And that's a case where if the system has translation symmetry, you can put it in an eigenstate of momentum. And if it does, in your frame, it will look like a time crystal in the sense that it's a macroscopic system, it's not losing energy, and you're seeing stuff which is periodic. So this is what you might call a symmetry protected time crystal. And these are not ruled out by the result of Oshikawa and Watanabe. They themselves discuss it in a different context, but this is a particularly simple one too. All right, so that brings us to, can you have symmetry unprotected time crystals, where it's not that there's some symmetry and you've done something with it, but there's somehow things are oscillating, because of sort of some other reason. So these don't seem to exist in Hamiltonian systems at non-zero temperatures. And let's come back to what is non-zero temperatures, but basically, if your system is going to equilibrate, right, it's not a time crystal. Because whatever you started it off with, it sloshed around and so on, and it settled down. Once it settles down, anything that you measure is time independent, it has no interest in time dependent. So to the extent to which you think that systems are going to equilibrate starting from fairly general initial states, you shouldn't expect to see a time crystal. Time crystal is really something, to take my favorite example, I've got the water bottle, right? And of course, if I just shake it and put it down, it settles down pretty quickly. It equilibrates. The next person walking doesn't know that I shook it. Time crystal would be I do this and it keeps doing this for the next 20 minutes, right? So that the person who comes in knows that we don't expect that enough. So that is, of course, going back to all this stuff with the second law. So, okay. So they had a proof in which they imagined they started with the Gibbs state, which is where the temperature came in, and then they showed that it couldn't happen. Anyway, the initial proof actually wasn't right. And when we pointed it out, they produced another one. The physics of the proof is still not clear to me, but the answer is reasonable because it basically was said things. So that seemed to be the end of the story in 2014, which I would have characterized as Carnot 1 and Wilczek 0. But then we were completely independently working, right? I'm describing to you the work on Floquet systems. And so that, of course, is the context of localization, and we are driving, but most importantly, localization, where, as I mentioned, those are not equilibrium systems. And so, of course, none of these objections sort of applied. All right. So now I want to go back to the time crystal phase that I introduced in the Eisen model. And so when I introduced the model, I said it was an Eisen model. And that was because both pieces of the Hamiltonian had Ising symmetry. One of them was ZZ, so if I send Z to minus Z, right, that term is invariant. The other term was X, and the way I send Z to minus Z is to act with X, and obviously X continues with X. Now, what's interesting is that phase, which you find by examining an Ising model, actually has what we call absolute stability, which is to say, once you found it, which was in this phase diagram that I drew, you can add any weak local perturbation that preserves the period. Right? So you've got some period, right, total time over which you're doing it, and you add, imagine that you've got a time-dependent Hamiltonian, which had two pieces, right? It's constant over one part of the interval, then it had another value over the other part of the interval. Add any weak delta H of P. The only thing that's necessary is that have the same period, not going to change the period. So as long as you had a many body localized time crystal to begin with, the perturbed one is also in many body localized time crystal. The starting Ising symmetry that we use to discover it is not important. Now, there is an example of this, right, which is not the topological order. If you have the toric code, for example, and you start with the toric code Hamiltonian, it's written in a certain way where, it sort of looks, you've got lots of structure, you've got these commuting operators, this, that, so on and so forth. But in fact, if you take the toric code Hamiltonian and add an arbitrary weak derivation, it doesn't have to be translationally invariant, it could be a 17-spin interaction, right? The topological phase of the toric code is stable, there's degeneracy, it survives up to exponential fitting and so on. So for time-independent systems, the topological order in the sense of the toric code is absolutely stable. The only thing you have to do is to keep to the framework that it's a time-independent Hamiltonian and locality, and things stay the same. And this is analog in the time domain, which is to say, as long as you keep period 2 and you add an arbitrary weak perturbation, the phase state. I really do want to emphasize that this is a big deal, which is to say, it's not like cases of symmetry protection where you break the symmetry, it stops being. Okay. All right. So I just want to give you a little motivation for why this is true without going through in detail. Yeah.
Yeah, so by weak, like if it weak compared to like this average J and average gamma, the previous slides we had, or
Yeah, I mean, well, okay, you also have to think about the variance. It's really this is the localization, which also cares about the variance. So, so the way to think about it is, supposing I worked out the initial phase diagram, as long as I don't sit right at the boundary and I sit some distance in, then there is some range over which it will be stable.
oh, okay, I see.
So local is spatially local, which is to say, so I have a spatial factor. In this case, I'm making up a 1D chain. The local is, any term in the, so say I perturb the Hamiltonian with some delta H of T, and the terms in delta H should not involve acting on more than some number of figure in a certain range. So not in the usual sense, not infinite range, not power law.
But this is still a system that has domain alteration.
Well, it does in the state, but not in the Hamiltonian.
Okay, because I was wondering in the actual state, basically have to have a range that's short compared to the
No. That's, I mean, there are certainly states with a very high density of terms. Yeah, no, we do not need that. Yeah.
All right, thank you.
Okay, so just to motivate as to why some remarkable result like this might be true, let me point a few things about this very simple idealized drive that we've discussed before. So remember what this unitary looks like is it's got a piece that looks like evolution with the Ising exchange, and then a factor which is just the operator that flips all the states. Right? So that was our, along that line on the border was our sort of model unit. Now, this one clearly has an Ising symmetry. If P is the flip operator, easy enough to check that P dagger U, P is U. So for instance, I write this here, stick a P here and stick a P here. Well, P squared is is 1, so I drop these two. But if I take P past the e to the I JZZ, well, because ZZ is Ising invariant, P commutes with it, so I can bring it to the left and then back to where I'm. So P dagger UP is in fact P. But here's another symmetry. Imagine I combine the Ising flip with complex conjugation. So this is now an anti-unitary symmetry. I claim that this anti-unitary symmetry, in the manner of anti-unitary symmetries, turns U, which is the time evolution, into its inverse. That's what time reversal type things should do. So how do you check that? Well, if you stick in here, a K, and then stick in here a K, what you'll find is that as you take the complex conjugation past, you're going to flip this I to minus I. The rest of the P's don't care because they commute the K. And so you'll end up starting with this one and ending up with the minus sign there, which is the inverse of the So this is a symmetry and this is a symmetry. Now I can replace this P, which is a product over X's, by a product over Y's, and a product over Z's. I have to restrict to even length chains, which is a little annoying. But nevertheless, where I thought I had one Ising symmetry, actually I have another 3 anti-unitary Ising symmetries, meaning they're all symmetries with squared one. So it's an unusually symmetric drive. And what's interesting, okay, all right. So good. Let's leave it at that. Okay. So the idealized drive is highly symmetric. Now, I can perturb that drive while preserving one of these symmetries. So let me give you an example where I'm going to perturb it by adding something that clearly breaks the original Ising symmetry, right? Because it's a longitudinal field. If you were doing Hamiltonians, you would say you put on a magnetic field, you no longer have Ising symmetry. But what happens is it breaks P, but it preserves this theta X. Okay. And tiny algebra, which is, first of all, you observe that if you try to transform it using just P, because this is Ising odd, you would end up with a minus sign here. But if you add the complex conjugation, this I goes to minus I. And then what I'm checking in here is that the new object times the old object is actually 1. And that requires you to take this P and move it past. It will flip H, leave J the same, kill P, and then end up with e to the minus I JZZ plus HZ and e to the plus I JZZ plus HZ, and then we end up multiplying to 1. Okay. So there's this sort of aspect that I can break the Ising symmetry that I thought I had while preserving this anti-unitary Ising symmetry, which at least initially I didn't want to have, and so on. So it's a sort of special drive where I can go off in various directions. So that part it was already surprising. What's really surprising is that you can add an arbitrary, let's say, combination of a Z and an X and a Y, and ultimately anything else. Now, there's no such exact thing I can find, right? But if I go study the spectrum of the unitary, I'll find that this pi pairing actually is there. Make the system bigger and bigger, becomes increasingly exact. And the explanation of that ultimately all is that, at the end of the day, I can add here anything I want as long as it's sufficiently small. Effectively, there exists a description with new Z's in which the whole thing just looks like P times e to the IJZs. But now these new Z's are emergent. They depend upon particularly which coupling they're putting in the first place. Here, I just tell you in the classical fashion what the symmetries are at the start, right? But an inversion symmetry, I can't tell you at the start. They used to have another name. I think we used to call dynamical symmetries in the old days in nuclear physics. Now they're called inversion symmetry. And it just happens. The SO4 symmetry of the hydrogen atom is a dynamical or emergent symmetry. It's specific to that. So, okay, so it's an utterly remarkable result. If you buy localization, it's not that hard to convince yourself of it. It's in this paper with the third. But that's the heart of the matter. That's absolute stability. So again, I really do want to emphasize this. Very striking, very surprising. When we first found it in numerics, it was seemed very odd that something like a doublet structure was present for no obvious symmetry reasons, and that it turned out to be. So Okay, so back to why the pi spin glass is a time crystal, of which I will give only one argument. So remember, at some stage we were talking about, the late time ensemble and having matrix expectation values of operators. So I used to have energies. Now I have quasi energies because they are eigenvalues of the unitary, so you don't call them energies. And basically, it's the same. It's alpha and beta. And what's going on in here is that, remember, I had this quasi-diagonal, this block diagonal ensemble in which I kept energies which were the same. Now for Floquet, I have energies in this particular problem which differ by pi. Right? That was the pi pairing. So if the number in here is pi, this factor e to the I n t times pi just becomes -1 to the n. So the same sort of reason, which is you go to late time, all sorts of stuff averages out. There are some special states. In the Hamiltonian problem, the special states were either in the paramagnet and a unique state, and that was it. Or for the case of the spin glass, I have these doublets with zero splitting. For the pi spin glass, I have these pi doublets, but they are perfectly designed to give you an oscillation which doubles the period, because the pi translates through this to a -1 to the. So it's exactly that same sort of arithmetic. So what this says is, if you start with something and you wait a while and you examine the expectation values and operators, what you should expect to see is a period doubling in which it looks to you like the red configuration turns to the blue, back to the red, blue, so on and so forth. And so you have the dynamics has a period capital T, but the state has a period twice. Yeah, very.
Oh, very nicely. I would have thought that a pi spin glass would be a time glass and a time crystal. What's about that?
So the glassy aspect is in space,
Okay. Oh, not in time.
not in,
Okay.
yes. It's a glass in space, but it's a crystal.
All right, thank you.
And can I put a-
Yep, please.
When you add these perturbations, they're not the,
Right.
you still have, you say you still have perfect staggering, or is it going to be some?
You have perfect staggering in the sense that anything you measure will have perfect staggering. Of course, these pictures suggest that I'm measuring Z. And when I add a general perturbation, what will happen is, if it's just very weak, the stuff will be fairly close to Z. But in fact, I can, so there is there's this sort of rotated Z's, if you will, not only rotated, but also somewhat spread, but the period doubling is exact. So that's a spectral feature that you can figure exactly what operator is the best to detect it, sort of evolves. Yeah.
What would a time glass be?
So if you just have the standard MBL problem, right? So now what happens is, the MBL more or less ends up being, you've got these local templates. In some sense, it's as if the chain decouples into independent spins. Each one of them sees a different field, and these fields are incommensurate. They have no particular relationship. So now what happens is, but it's a bit worse. It's not just that they're independent spin. What happens in an MBL state is that the energy of one spin, the energy function actually does depend on check write something. So basically, so the thing is, so let's say you have these L bits, let me call them tau Z's. So the statement for MBL is that I've got an energy function that looks like HI tau I Z, so like a ring of feet, but then I've got a JIJ tau I Z tau JZ, with some 2 spin term with some decaying envelope, then some 3 spin term, but all of them are Z, so they all commute. Okay? So what happens is that if you flip a spin, you end up picking up what you flip is not an L bit. If you had an exact L bit operator, you would get only its frequency. But you have a physical spin which has a weight on many L bits, so it picks up a lot of frequencies, which are incommensurate, but they sort of die out as you go away from that point. So these are sort of these, so you get one large frequency, then a few smaller ones, and then even smaller, the distribution. right? It's like these almost periodic functions that you of course probably calculate or something. And so because they're incommensurate, the actual time trace is not periodic. It's got some effective number of frequencies which are sort of incremental, but ultimately an infinite number except smaller and smaller and smaller. So that's what the time glass looks like. But but that holds for operators which are sort of, you sort of measure autocorrelation. So an NDL system in that sense is a time glass.
Thank you.
Okay. All right. So okay. So good. So let me now talk about experiments. So one thing I want to emphasize is this discrete time crystal or pi spin glass is actually a wonderful place to try and detect. One, it doesn't, you can give it a large class of initial states, and after a while it will give you these oscillations. So there's a lot of robustness with respect to the choice of initial state. Then there's robustness with the choice of Hamiltonian, right, which is also nice because you don't have to perfectly tune it, right? And so on. So the fact that it's an absolutely stable phase and the fact that it's eigenstate ordered with the entire spectrum being implicated actually makes it a wonderful thing to try and see, which made it particularly disappointing that the initial experiments did not do this. Right? Okay, so one of them didn't have a choice, but the other one actually did. So the initial two experiments, there was a third one at Yale. One was by the group of Chris Monroe, and the other was by the group of Michel Lukin, including my younger collaborators. Okay, so what did they do? So somehow pictures like this show up in this game. All right. So what did Monroe's group do? So they had a set of 10 spins. Actually, let me describe it. Okay, so Monroe was trapped ions, 10 of them, and Lukin's was millions of NV centers, which also were sort of, so both of them were spin and a half systems. So what did they study? So the Monroe group studied 10 spins in ion traps, and certainly for the time, since now they've made a lot of progress, struck me as being a real experimental sort of tour de force. So they'd certainly initialize their ions in, which are basically eigenspins, then implemented this drive, and then measured individual spins so they could sort of calculate the autocorrelation function. Okay. The only thing is, they only did this for a single initial state, and that initial state was sort of all spin up. Yeah. That was one problem. This was particularly important because they were actually limited in what disorder they could introduce. They were able to put disorder in the form of a random field, but not in the form of random pots. Now, it turns out that if all you do is put in random fields, those are extremely inefficient at producing many-body localization. To zeroth order, they cannot produce many-body localization. And that is related to this anti-unitary symmetry type stuff that I've said. So in the Hamiltonian or in the unitary drive that they actually implemented, all spins up gave you a lot of oscillations for many periods. But supposing they picked a very random sort of spin configuration, they would have found very little work. But since they only picked the one that worked, they didn't notice that that most of the spectrum wasn't going to cooperate with. Now, as far as the Lukin group was concerned, they basically could only produce a fully polarized state. They had lots of spins. On the other hand, they were in 3 dimensions, and I think we were having a discussion earlier of the fact that localization is problematic about 1 dimension. There are also long-range interactions with the system. Localization is problematic, even more so for long-range. So they never said they were going to see the many-body localized time crystal. They said they had seen a critical band crystal and came up with the theory of it. But that doesn't have true long-range ordering time anyway. And again, they were restricted for their own reasons to start with a single starting state where all this went through. And then the Yale group saw some stuff in an NMR system, which we eventually were able to understand. So the problem with all of this was that what was the most interesting aspect of this proposed phase, which was eigenstate order, the fact that all eigenstates were implicated, right? That had not been seen. And I mean, it took a while to persuade people that, there was still something interesting left to do. My own judgment, the central interesting thing left to do, but eventually, when the Google group put out its quantum supremacy claim, we looked at the gate set that they had implemented and realized that there was a good chance that they could do this constructed. Unknown to us, there was a group at TU Delft which was working in parallel, but I won't describe their work. It's on a smaller system, but goes longer in time. Okay, so basically, right, Google's platform abstractly has qubits, there are gates that they can do, and there are measurements that they can carry on. So schematically, they're able to initialize an initial bit string on the chain. For us, they used a device with 20 qubits. And so, that says 0, 1, 1, 0, so forth. Then they can act with single qubit gates, which is this piece, which is the transverse field. Then they can act with a bunch of interactions, which is here. What I was calling Ji in this paper was called phi. And then also a set of longitudinal fields, because the way their gates are defined, easier to stick them in. And because of absolute stability, it really doesn't matter. These longitudinal fields are particularly cheap. They don't do much. So this is then the Floquet unitary that they're able to implement. And of course, they have qubits, they do this once, they can do it twice, 3 times, 4 times, whatever, run it for some number of cycles, and then simply read out the state of all right. So that's abstractly what they are able to do, and I'm about to lose power. Why is that? Shouldn't this be charging it? So for some reason it isn't charging it. That worked.
Sorry, I have a question. So what's the difference between this and what the Monroe group did? Was it the middle thing?
I mean, so Monroe was, first of all, it was ion traps. So, they had these power law Ising interactions that they produced, right? They didn't actually have the capacity to do 2 gates at a time. So one of the issues, and then of course they couldn't do this these random bonds.
So the middle.
Yeah, that's right. And that's very important because without it, you don't get NBN.
So would the Google experiment work if there wasn't randomness in H?
Yeah, that's not important. That's it. I mean, we can live with it, but it wasn't. Yeah, exactly. Okay, so I think I said everything I have to there. Okay, now that's the sort of abstract view, but of course the actual platform, isn't a perfect quantum computer, right? So the various things to check. One was, of course, you're going to see something for 20 qubit, you're going to see it over some period of time. Just because you see a graph with a wiggle, you can't say that's it. Right? So at the very least, you want to be able to say, sometimes I see it, and when I don't expect to see it, I don't see it. Right? You want to be able to see both things. Then you have to have some way of saying, well, okay, I've got a finite size system, but in fact, as I increase the system size, I see that evidence will be better. Then the actual device has a finite coherence time. The qubits are, let's say, a third. And so you want to convince yourself that the phenomenon that you're seeing is longer lived than the limitations that are imposed by hardware. So, okay. And finally, you really want to convince yourself that there's eigenstate order across the spectrum, and even at 20 qubits, you're talking about a million states. And of course, you'd like to be able to, in future iterations, go up 50, right? And at some stage, you don't want to be sitting there doing, preparing these items. So you want to find a way of doing this without preparing every single initial state, every single bit. Okay. All right. So in the experiment, you initialize the state, you run it, you measure it, and you obviously run it multiple times, and you can get a plot of different times. So what's going on here is you've initialized the qubits, and you're measuring the z-value at some later instant of time on qubit 11, which is in the middle of this chain of 20. It's been done at two different values of G. G have to do with this transverse field. This one is where the time crystal should be strong, and this one should be very weaker. And you see that actually it's weakened a lot. So we believe that by the time you get here, also supported by separate numerics, that you are by now in a thermalized field. So it's a question of, you had this flip that you were doing, which was very close to pi. Now you're doing a flip which is not that close to pi. And as the flip gets increasingly far from pi, at some stage, you leave the phase. Okay. So first, if you look at this and say, well, clearly in this phase, the expectation value of z decays rapidly. In this phase, it does not decay rapidly, and we've gotten up to 100 oscillations, and it's nothing there. Now you can do better than that. And this is one of the ways in which this quantum hardware is really quite neat. It's easy enough to run something forwards and then run it backwards. Right? So if what is going on is external decoherence, which is the fact that the qubits are stuck in the middle of the solid and the phonons and this and so on, well then you lose coherence on the way out and you lose coherence on the way back. Right? So the echo experiment is one in which you run it forwards and run it backwards and ask, I started with z equals 1, what is the value of z when I come back? Right? That's the black curve. This one is what happens when you only, as it were, you got to take a square root or something. If you, but this is what's happening when you're running it forward without the echo. So you see that when you're running it forwards, the autocorrelation decays much faster than the effect of decoherence that you guess from running it forwards and back. So this is a genuine physical effect in which spin number 11, because it's sitting in the middle of a thermalized system, is losing coherence, not because it's talking to phonons in the device, but because it's talking to other spins and sites. So this is very elegant because it's something you can do as a result of the hardware.
So a factor of 2, right? One is 10, one is 20.
Here, well, you want to compare these curves. So in other words, this one decayed very rapidly. This is my
Oh.
What temperature are you measuring?
Well, so there's some device temperature, but I think in this case, because it's I'd have to look it up. I don't think that's germane, because what you're really doing is initializing a state and then acting with the Hamiltonian. So it's really, like only these degrees of freedom are relevant. The temperature of the surrounding device is relevant in the sense that this decay has something to do with the fact that the rest of the system, it will enter the dephasing of the qubits by the rest of the system. Right, and I don't remember what it is. Yes, I mean these are traditional superconductors, so they certainly have their operation.
The errors in superconducting circuits, there's a lot of stuff about them coming from non-equilibrium. It wasn't fun, like trying to work out what the non-equilibrium source is. So the error rate is actually, it's not directly connected to what the temperature of the stuff is, which is another question.
But presumably they act. What is the TC for this? These are I forget.
I don't know. They're like really cold. I think it's this black curve is the thing that should.
Yes. All right, good. So what, all right. Lenovo recommends. Oh, no, don't. Yes, okay. It's trying to update, Mike.
Question.
Please stop. Thank you. Yeah, question?
I mean, if one does echo without knowing what the path is, that gives a sort of extension of lifespan, like coherence.
Mhm.
And this is, I guess, coming from the interaction between the qubits. So,
No, so this is coming from the interaction between the qubits.
yeah,
This is coming from unknown stuff in the device. So the point is, I see, right? I mean, going forward, I see a very rapid decay, but when I do the echo, I recover most of it, right? So it tells me that it's, like, spin echo or something. It tells me that the actual coherence in the system relative to its environment was much higher. I was just losing information to other spins, which I can recover. What I can't recover is information that I lose to the rest of the device.
but usually in a qubit, in an artificial qubit, one does recover some of that as well. There's
Yeah.
some of that recovery there.
That's this curve, the black curve. Right. It's what you get back if you nominally go forwards and nominally undo it. Right. And if this was exact, you'd get back exactly the one, then this curve would be flat. It isn't flat. So it's got some characteristic timescale, which you can associate with this extrinsic decoherence. Then this timescale is intrinsic decoherence. So what is the thermal phase of our system? You see that the intrinsic decoherence is much faster than the extrinsic decoherence. In the MBL phase, which is where the time crystal is, what you find is that, in fact, the estimate from the echo pretty much matches the decay. So there, you see that you're limited by extrinsic decoherence. Right? The system looks like it's localized, and it's only the extrinsic decoherence that's getting here. So if you could improve that curve, you would expect to see oscillations going on, more or less undiminished.
But this black curve is really decoherent and not finite. More important, there's two options before.
Yeah.
One is more important time.
You
said there were two real experimental treatments, finite system and finite decoherence
Yes,
time.
yes.
Which one is more important?
So in this case, the finite system is shown. We're just limited by hardware. In fact, that's right.
I'm sorry, and how many qubits do we have? And
20 of these experiments. Yeah. I mean, they had 50 qubit devices, but this was not considered important enough to. I understand. I mean, it's interesting. They really are focused on building a quantum computer. So the most high priority items are ones which involve actual computational uses, which is fair enough.
you've got about 20 minutes.
I've got about 20 minutes. I should be done. Okay. So I said we wanted to actually average over all initial states, right? I want to check that the entire spectrum has this feature. So for this, we use a neat trick, which is called quantum typicality, which says that if you have a random state on your Hilbert space, and you calculate the averages of operators in it, all the off-diagonal stuff goes away, and basically you get the expectation value is very close to what you would get if it was not a coherent random state, but an incoherent mixture of all bit strings. Okay. Random, just pick it randomly with the unitary measure, the hard measure within the string. So start with some initial set and act with it on a 2 to the n by 2 to the n unit. So, okay. All right. So what this means is that while what I'm interested in is take every initial configuration of spins, evolve the system, measure it, and then do a sort of classical average, which would require me to go through 1 million initializations. I actually don't need to do it if I can produce an initial state, which is actually a coherent superposition randomly picked over 2 to the n states. Right? Now, fortunately for us, because this is what the Google quantum supremacy experiment was about, just to simply acted with some number of layers of unitaries picked randomly to produce a random state. And then they looked at it and they looked for evidence of there was a Porter-Thomas distribution of the eigenvalues. So that's great. The output of that quantum supremacy experiment became for us the input into our experiment. And there was one more thing that had to be done, which is another of these really clever quantum computing techniques. And that, I think one's appreciation for everything that's been developed really starts to go up when you see the clever tricks in operation. So what you do is you start with a bit string, you have this sort of approximation to a random unitary, which is going to give you a high random state. Then you have two controlled Z gates. So there's an ancilla qubit, which is initially polarized in the plus X direction. And then the control says, if in the Z basis this one is 1, then you do nothing. If in the Z basis this one is -1, then you do something. So this is where this is written. So just focus on equation 22, which is when the ancilla qubit in the Z basis was a 0, whatever state I had for the system, right, which was produced after doing the initial sort of scrambling, stays where it is. If it's 1, I act on the system on that particular bit number 11 with a Z. Then we evolve the system with a Floquet drive for T periods, which is, so this is to the power T. And when you do that, you get a U to the T acting on psi, and then a U to the T acting on Z times psi. And then you apply another control Z, which, like here, has the effect of sticking a Z in front of the state that you have multiplying when the qubit is 1, when the ancilla qubit is 1. Okay. So that's what you end up with, 23, at this point in the circuit. Now you just measure the ancilla in the X basis. When you work out the expectation value of X, X connects 0 and 1 because those are both Z eigenvalues. So it's just the off diagonal element, which is this. Notice that this is Z, U, Z, Z, U, Z, and then the dagger of this, which is here, and then plus the complex conjugate. But this combination, U inverse ZU, is just the time evolved version of Z. So in fact, this is nothing but the autocorrelation function of spin I, produced by measuring this ancilla. Okay. And then because the state psi where you began was a high random state, in fact, this is the infinite method for that. So in one shot, you get the autocorrelation function of, let's say, the 11th spin with itself, with time t, average over all possible. So this method obviously scales. You can go for 20 qubits, you can go for 100 qubits. So it's really very neat. And so we were able to do that also. All right. So the upshot for all of this is that this bi-spin glass, Floquet time crystal, discrete time crystal, you can see it's a particularly nice phase because it was renamed twice. So it's the first genuinely Floquet phase in a closed quantum system. It's also the first example of finite state order. And in steady state, when it settles down, it does not extract net energy from the drive and breaks the time flat symmetry. So I think it's okay to call it a time crystal in the sense of a macroscopic conservative clock, although obviously it's nowhere near as neat as it would be if it was in a continuous time setting. All right. Now, exit. Now the question is, I'd like to show you something else, and the question is, can I? All right, now stop sharing. Let's try again. Screen. This time it's PDF. Maybe it'll work better. No. I have to say, I have no idea how the chart here is. It's funny, somehow between the morning and now, I've lost my capacity to be back with that. Okay, try one last thing that might work. Let's close PowerPoint. Save. Let's just try this. This I don't understand now. Don't. Ay, 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 ay. Anybody have any insight on to do? Somehow it's not, I'm not able to get it to recognize the screen 1, screen 2, whiteboard. Okay, I think I'll just say it in words at this point since I don't see this working out. Last try and I'll give up. No, so, never mind. Okay, so I'll just say it in word. Okay, so the last thing I wanted to say was that, you know, one of the lessons, at least to me, of, you know, working with this Google Steam and their hardware is, you know, this aspect that these advances in hardware platforms, you know, they're really quite impressive. And, you know, we've sort of gotten to the point where they can do things, they have a degree of control, which is really, you know, quite striking. Now, of course, the rise of artificial quantum systems, like many things, it didn't just begin yesterday. You could say that the two-dimensional electron gas was probably the first really interesting, you know, artificial system, and it resulted in some spectacular number of discoveries. You know, certainly the two quantum Hall effects, you know, would not have been found had it not been for a very controllable platform. Cold atoms, obviously, you know, came next, and a lot of good of the stuff has been done there. And so these certainly follow in this sort of tradition of getting increasingly controllable ones. Nevertheless, what's going on now with these, you know, so-called NISQ devices is, of course, that, you know, that because of the computational interest, there is a very large sum of money chasing them, which means that there is a very large number of smart people around the world, you know, who are very well incentivized to develop. So I think over the next 5 to 10 years, I think we're going to see pretty spectacular advances in what these devices can do. 50 qubits, certainly 200-300 qubits. I imagine, you know, we'll get to things which are very highly controlled, and a lot can be done. There are plans for devices with 1 million qubits, but, you know, the question of how quantum coherent they are is a different one. Now, the nice thing about these devices is that you can make a gate set, you can do certain unitaries, you can do certain math. Because quantum mechanics is about unitaries and maths. In that sense, what have to be done. Now, so from a many-body physicist point of view, quantum circuits and measurements, you know, it's sort of the toolkit economy. Now, historically, we focus on time evolutions, and then we measure once because measurements are sort of complicated. But now, with these devices, what's coming in view is the idea that you do measurements, and then depending on the measurement, you do something. Okay? They're not quite in view yet because measurements take time, and none of the platforms currently are able to quickly do measurements enough before other aspects of quantum coherence are lost. But you know, they're working on it. That's after all what quantum computing is about, right? You measure something, you error correct, so on. So it generates this very interesting area, which I'd like to call quantum interactive dynamics, in which you talk about, you know, many qubit systems, which and their possible time evolutions, which involve this interplay between measurements and evolution, right? Now, at some level, this should be nothing new because that's the toolkit of quantum mechanics. But on the other hand, some effective time evolution, which is in some ways nonlinear, and as to whether you can get steady states, whether you can get a certain kind of steering, whether you can find special phenomena, I think all of these are really interesting. So what the time crystal stuff showed was that you could gain by having the capacity to make symmetry circuits. There's a lot of work on these so-called measurement transitions, in which you have a simple competition between unitaries that build up entanglements and then measurements which disentangle. And it's been discovered that you have a certain critical density of measurements, you destroy coherence, entanglement, and therefore you end up in area law phase. If you don't have enough of them, in volume law phase. But that's still with the measurements being basically dumb measurements, in the sense that you're not just measuring, and then the evolution is uncorrect. But the next step is to put them together and see what will happen. So I think we're talking about sort of a fundamentally new kind of physical system, right? Which is this sort of quantum device and a classical computer, in very intimate dialogue, and sort of driving each other in some direction. And it's an interesting hybrid system which is coming into being. Algorithms are particular evolutions which can run in this system, which are interesting for others, right? But if you think about it, presumably that's only a small class of things that such a device could be. And my hope is that many more of the evolutions that such a hybrid system are capable of will be interesting to us as many-body physicists, than would be interesting as algorithms. Maybe it's not an algorithm at all for anything, but on the other hand, we might look at it and say, how neat. The time crystal doesn't solve any problem in computation, but it's interesting to think about it. So anyway, so my general hope is that in the next few years, as hardware progress continues and the $10 billion plus which are chasing devices are usefully spent, that many-body physics will evolve along with it, and then we will come back in 10 years and have a whole set of results on quantum interactive genetics, which will write hopefully another glorious chapter in the history of many-body theory. For those of you who are on the younger side of myself, I encourage you to think about this area in mind. Working. That done. Speaking of platforms, as you can see, with quantum computers, I won't be able to share my screen at all.
Interesting, in the context of quantum simulation, talked about the two-dimensional electron gas. I mean, do you think there's the nature of discovery? There's some robustness which the fraction quantum Hall effect exhibits. Which is, even though the samples are dirty, we don't know a lot of physics. There's some notion of universality, not in a in a more sort of not mathematical sense, but the NISC devices sort of on that measure, where do they sit?
Look, okay, so let me say something related and come back to what you're saying, which is, so I think I think going forward, there will be two kinds of theory. There are two kinds of theory which are done at CERN. One class of theorists spend their time at CERN simply helping find new things in the data. Right? Their job is to rule out the standard model says X, that's the background. Do you see anything about it? So we 2 months here. You think they found something, it often goes away so far, maybe a couple of anomalies now. And that's because the CERN accelerator is an incredibly complex device, right? And it takes a lot just to understand the background before you can think of the stuff. So I think there's going to be a class of theorists for disk devices whose job it will be like CERN to sort of see, when when these things run, right? That what's the boring stuff? It's because it won't be able. And then on top of it, you will be looking for new things. So one mode is that the classical computer and the quantum computer do the following. The classical computer has been programmed with some cost function. Some theorists have decided, it's like triggers in CERN, something will be interesting. Like for the time crystal exposed factor, I might have said, start with an initial state, run it for steps 100, 101, 100, 200, 304, check whether the initial value Z has oscillated. And if you find a circuit that's doing it, fiddle with the circuit till that signal becomes stronger and stronger. So it's a kind of sort of gradient search with a certain cost function. So I think, so one, that's like triggers, I think it's also. Now, the hope would be, of course, that periodically you find something completely new. And that's where your robustness question will come in. And when that happens, then there will be improvements in the string theorists who will say, all of this shows that, the paper I wrote last week with the 1700 representation formulated from the monster group, that's exactly what you're saying. The only difference, so that's, I think, so I think one aspect of these devices will be, they can do lots of things themselves. It's to simply decide when something has an interest and when have you seen it on conflict. Whether it will turn out to be robust or not, then we'll discover by looking around. I think that both kinds of physics, there's robust many body stuff that's generally most interesting, and also the hydrogen matter. I wouldn't necessarily rule out and finding very special things which you have some initial state and you run it and somehow that information follows and you don't know and get up and no, it's looking very perfect. Very different group of them. So I think it's an interesting huge where the gospel theory. Yes.
Can you say something about the accessibility? I mean, you said it was not considered important enough to give you more qubits, and I guess people who are interested in developing quantum computers don't care about time crystals at all.
So,
so is there a proposal stage or something that people can submit ideas? So is it decided by the panels or?
Yeah, so it's a little bit informal at this point. So I don't tell you exactly how we got to on their program of needs, but all of them, of course, and they're all putting their devices to some extent online, right? With the new other people that sort of play with them. I think somehow when you're doing pure science, typically, we'll see. If the ones online end up being very, very accurate for practical purposes, maybe. But yeah, it was certainly we could not have done an experiment had we not been closely collaborating. Because there were all sorts of things, all sorts of people with venue their devices, with really kind of more dedicated to the point. But so we'll see. Maybe like supercomputers will be national. The facility is, but I imagine the frontier will always be the devices. Not everything to be working.
Do you think in the future there could be some operational model like central facilities where
I think it's like
it also applies to explore fundamental science, or
since it worked for supercomputers at the start, that's how it used to work, even for today. You don't typically use supercomputers because not all work for all sorts of purposes, but of course there was a period when you didn't have access to a trade and certain, and even today things you can't do on it. So I think it's we'll see. The question is, when you have quantum laptops which are good enough, see the Hilbert space goes exponentially, right? So in fact, you could imagine that a 200 people laptop would give you a lot of time to spend storing. You don't want to know laptop. Or maybe like to make the machine. I don't know. These are all. I'm proceeding by analogy, but I can tell you about it. That was at this point, they had sort of an understanding of the error model, decoherence was super. These were all sort of important things that they had done the echo stuff somewhere else, and we do that, and we add some stuff. It's a very actually very enjoyable, fruitful collaboration, but it's a fact that they love it now.
So I have two questions. One that you've already alluded to. I was going to ask, how do you know this way you to do this experiment? Because this isn't straight quantum computer. I know from my time at NC when it's lab
Yes,
tried to get them to make a Josephson array,
Right.
we could not because we said that this wasn't a hyperarray.
So,
And then the second question of the
Yeah.
day is, were there any surprises in the sense of challenging the theory that we had with their experiment? So, number one first.
so the answer to the first part is that so far, many of these quantum platform developers have been interested in physics applications and capability to understand. Just very good, and so especially if it ends up in high profile applications and a larger community notices that have that. So I think, but of course the bar for them keeps going up because that's not what the company is looking to do. So I think that's the second thing that you said, I think is entirely fair, which is to say a lot of what has been done so far, the thing that we almost all of it, is of the nature where you sort of understand the theory fairly well. And then when you do the experiment, you sort of confirming that the device does that. Now, if they would lend us their 50 qubit device, there's just no way we can do that. Okay. Not the limits of classical computation also can move with algorithms, but certainly forgot how to many qubits, and then anything we wouldn't be able to do it on that. Right. So, as a physicist, I'd be very interested in seeing the 100 qubit macro. It's also, see something there in the detail, maybe incentivize you to think more qualitatively. So I think that's just a question of getting to a certain scale. I think by the time we're running an experiment, 200 people, we're going to be doing things which we have to now think about. But the other is that ultimately the value should be from discovery. It should be to find the analogs of the ground holocaust. And I think, in thinking about it, I think we ought to think about what, our traditional toolkit, in some ways, is fairly restricted. You pull something, there's some scattering, response for a treatment, actually the market is how far we've gotten with something. These guys, in principle, can measure all sorts of things. Right? And so, let me ask me what's interesting. In that way. That's it came back to the sort of cross country.
And say pre-June.
Yes.
So let's start the idea again.
Just get back to Oxford and mix the top on high pressure, because I thought we were all under high pressure, but the top were not to explain.
So 15 minutes or something. What do you think? Okay, 15 minutes break.
Yep.
Yes, I declare 15 minutes break. Yeah, and
So we can't use to get a copy.
that's the trouble because about 55 minutes long.
Yes, I see.
So I mean, with that 5 minutes, we come back into it. Might be worth playing 40 minutes end up each one of the words.
All right, good to see you.
Good to see you.
Yeah. I think that's tight.
See you.
Do we continue?
Archie?
Do you want to copy?
Yeah, we need some percent that are like, with paper. I think it's relevant.